Welcome everybody. Okay, today things are gonna start getting interesting. We are making we're gonna make the convolutional part of our neural network today. On top of that, just a few small changes. I've already committed everything I did last time to GitHub. I didn't do that at the end of stream, but I just did it a few minutes ago. So everything we've done so far is now on GitHub. And let's see, what else are we gonna do? We'll do some small things first. So first, I actually did do a few things here. Git checkout main. How do I do this? So I already streamed this a little bit, but I didn't show my screen. So I wanted to undo everything that I just did, and we'll do it live on stream, because that's the rule. Every piece of code we do, we're going to do live on stream. So without further ado, and I'll remember this time, here I am showing my screen. Let's see. Okay, I'll just discard changes here. And we will redo this. Perfect. Okay, we're back where we were. So first thing, we'll give our main function some breathing room. Let me see. It's asking me to change it. We'll use this old one here. Don't save. And let me make sure it's the old one. Yes, okay. Here we go. All right, first thing we'll do is, and I didn't do this last time, but on our GPU info print, we return a positive number if there's an error, and we return a 0 if there's nothing wrong. So let's go to our main function and account for that. So right now, all that we are checking is that if the GPU supports cooperative kernels, or cooperative groups is what they call it. And that allows threads to sync across all threads running on the kernel, which was a feature only introduced in the Pascal generation, which is the GTX 10 series. So if you have a GTX 10 series, even a really cheap one like a 1050, then you'll be able to copy all this code over. You'll be able to clone it from GitHub and then compile and run it on your GPU. If you have anything earlier than that, like a 7 or 8 series, well, they don't have an 8 series. If you have a 7 or a 9 series, then you'll have to upgrade your card, unfortunately. And as far as if anybody's running along, or if anybody's following along but doing OpenCL, I'm not sure if that feature is available. And then there's Apple's GPU code version. I don't remember the name of. But I'm not sure if it's supported in that either, but it probably is. Yeah, if you're running on the M1, since that's a pretty new architecture. All right, also on to the next thing. Let us change our directory delimiters here. Oh, and then we'll actually finish this thing. So if there's a positive number, that means there was an issue. We'll just comment, no need for print statement. Print comes from within this function here. we'll go ahead and we'll update our main project file. Okay. Now, let me think of anything. Try to think of anything else we should do right now. I already know it compiles because I just did all this. I only streamed for like 10 minutes. So I didn't do too much, but I will prove it to you that this compiles. Right now we're just C making it. This is for our actual project. Now we'll build and run for our main, our real main. Looks good. Okay. We still have this linker warning, which we'll look up later. And we still have that CUDA bug. If we run over 128 threads per, or blocks per grid, then the kernel code does not execute. And it doesn't even spit out a warning error, unfortunately. But I'll show you. All we have to do is reduce it to 128 blocks per grid total, and it'll run. There we go. All the way to over 16,000 like we want it to. Which is fine. We can run 128 blocks with 128 threads per block. That's more than enough threads for us at this time. All right, so here we go with our neural network. First, we'll create our block size. So this is the number of threads per block that we'll run on our CUDA kernel. We'll have that at 256, and we can experiment with that once we begin optimizing our code. We also need to define. We should use these definitions to define our neural network. That way, it's flexible, and we can later change it easily to other formats. So right now, we're just doing the MNIST handwritten digit recognition, which comes in at a 28 by 28 square of pixels. That is just grayscale, so white to black, and like gray in between. That is an image of somebody that has written down a number. And that's not a picture of the somebody, but it's a picture of the number. So in this project, then that means our input dimension is 28. So we need to know the total amount that is, which will be just our input dim squared. And now we'll start characterizing our first layer. So out of all the models of our paper, an ensemble of simple convolutional neural network models for MNIST digit recognition, this is a paper we're basing our architecture on. They compared a number of different neural network models. They did 6 in total, and their best performing one was this one, which is M3. So it comes in 28 by 28, and they use a 3 by 3 convolution with 32 channels. And they do that over and over again. It's just a series of 3 by 3 convolutions with the number of channels increasing by 16 every time. And then after they're done with that, they take all of the output neurons from the last layer, which would be So every time they do a 3 by 3, the output matrix is reduced by 2 on each side. And they run this, how many times? Like 10 times. So the final output is an 8 by 8 matrix, and it has 176 channels. So they take all of those elements and they do a fully connected network down to 10, with the only possible correct answers being 0 through 9. 10 elements, they bring it down to 10. And whichever number that was written down, optimally their neural network will have a 1 that corresponds with that digit, with that element number in their output array, and have all of the other output numbers be 0. So that's kind of a high level explanation. I've gone ahead and in AutoCAD I've created a depiction of our architecture. Just the first layer for now. All the layers are the same except for the last one. So this will get you a good way there, if it actually opens. By the way, I'm on Discord right now if anybody wants to hop on. AutoCAD is not one to load. I'm just taking a look at my live stream right now. There it goes. Wow, this is an NVMe SSD, so that took a long time. There's 2 of them running. I'll close this one. AutoCAD is my favorite application I've ever used in my life. I've used a lot of different software tools in my time, and it's got the best hotkeys and like the most power out of anything I've used, even between different IDEs that have a lot of features. AutoCAD was extremely well thought out. Okay, so here's the size of our input image. So as a refresher, I'll show you again what the data actually looks like. It would be, here's examples. They've literally just scanned in boxes that people had written numbers into. I think there's there's 60,000 images in the training set, and then there's 10,000 images that are for testing to see. So you train on the 60,000 and you see how good you are at predicting based on these 10,000. So you don't put the 10,000 through the training process, or else you could just be overfitting and thinking your neural network can generally solve it when I can't. So it's a 28 by 28, and we'll be applying a 3 by 3 filter across it. And I'll go ahead and kind of show you what that means. So we have our 3 by 3 kernel. What we'll be doing is an operation on a 3 by 3 space within the kernel. So do our operation here. We scoot over one, do our operation here, in here, and keep going until we've covered. And then when we get to the second row, we just move one down and go here. And what might this operation be? Well, it's that for each value, these each represent just one floating point number, just like these squares do. Our operation is that we will multiply the overlapping floating point numbers, and then we'll add them all together, and we'll put that in our output layer. And our output layer will also be 2D. So as I was saying earlier, we're going to reduce this 28 by 28 matrix to a 26 by 26 matrix. That's because this 3 by 3 only fits in here so many times. Like you start here, we go over, and we go to here. That's only 26, and same height wise. So we'll have our 28 by 28. And we will be applying on our first channel 32 of these filters, and we'll be getting 32 output matrices. So you see here they're 26 by 26 output. So what's really good about convolutional neural networks as opposed to fully connected ones is that there's much less weights that you have to store in memory. So for instance, on a fully connected layer, if we went by a 28 to 28, which is 784, to another 784 element layer, the amount of neurons we would have would be 784 squared, which is like get pretty close to a million. Probably, it's like 500,000. And that's a lot of weights. It's a lot of memory. Especially as our neural networks get very, very big, which for our AI art generator, it's going to be a huge neural network. With this method instead, with convolutions, we have these 32 kernels, but they're each just 9 floats long. So that's, what is that? Like 288, only 288 weights that we have to store. And we're using 2 byte floats, so that's only, that's like very few bytes. Less than, or about half a kilobyte. So once we get these 32 output matrices that are 26 by 26, we're just gonna add them all back up together again here. As a result, then we'll do a process called batch normalization, which is where we like squish in the outliers. So if any result is a really, really big number, that could screw up other parts of our net and layer their layers. If it's just getting a really, really strong signal, then we'll keep that from happening. With batch normalization, all you do is you take each element and then you subtract its mean, the mean of all the elements, and then you divide that by the standard deviation. So as you might imagine, that kind of, normalizes the numbers as it says here. And then for our next step, all on the same, this is all considered part of one layer. We'll have a ReLU activation, and we're using a custom one that I want to try. I made it up. So it's named after me. And it's the Mick ReLU. And with this ReLU, what we'll do is we'll take the output of each neuron, and if that neuron is between -1 and 1, it'll just keep its same value. If it's over 1, then we'll give it a small slope, and if it's less than -1 too, we'll also apply the same slope to it. So I'll show you what a typical ReLU, a very basic ReLU. Let me change the colors here. a very basic ReLU. It's just 45 degrees. It's just a 1-to-1. It goes on continuously. Whoops. And if the output is less than 0, then it just gets rounded up to 0. So this is just a typical ReLU. There's an issue with typical ReLUs though, and that is that when you're doing backpropagation, you're trying to find as you change a weight how it's changing, how it ultimately changes the output of your neural network. But part of that process though is taking a change in weight and seeing how it changes all the neuron values from that weight all the way to the end. So if you have that neuron value going into one neuron that eventually goes into another that is below 0 and is rounded back up to 0, it doesn't matter how much you change that weight, that neuron's not going to change, at least not from the perspective of like the tiny slice it can move around itself. I'll show you about backpropagation math on a different episode, but basically like the change that your weight will have to the output, you can only see from like from the exact position that all the neural network values are. So if you'd say, oh, if I change this weight a lot, it'll change this neuron a little bit. Well, that's only if all the other neuron values stay the same, but they don't. As you change one weight, all the neurons can start transforming in different ways. That's not caught in backpropagation. It's only basically if you just changed your weight a little tiny bit, like how much would everything move? But you don't change it a little bit. You change it more than that. So it's not completely accurate, but you do it over and over again, the backpropagation, and you tune your weights. And it eventually learns things, as is been demonstrated over and over. So the fact that if you're at below 0 with your weight or with your neuron activation, and not only it gets rounded up to 0, and as that neuron goes up and down in value and nothing changes, or its value doesn't change, is a problem. So what's common today to do is pretty easy solution. You just take if it's below 0, you just transform it up to a line that has a small slope. And this is called a leaky ReLU. ReLU being rectified linear unit. Also, there's other types of activation functions. The only technical requirement for an activation function is that it's differentiable. A previously common activation was a sigmoid function, which is it's a form of an S-curve. And no matter what your neuron value is, it'll put it between 0 and 1, the result. And this function here, 1 over 1 plus e to the minus z, z being the input, it's differentiable. But as you can imagine, it uses extra computational power to do this, so it's not used much anymore. And leaky ReLUs perform just as well, so there's no point. So just as further explanation, as we go and we convolute through our matrix over and over, as we get to the last place that will do the convolution operation, you can see this is a way to show that we'll be multiplying them together and then adding them. Okay, so without further ado, let's get started. So I'll start off the definitions for our first layer, characteristics. I'll begin it with first layer instead of something like layer 1. So that way the auto completes faster. If I just type in FI, I can auto complete. So first layer output dimension is 26. Control C, Control V. So these numbers we'll be using in our convolution phase. This block of 3x3, it has a few names. I'm gonna call it filter. Some people call them kernels, but we have a name for kernel with CUDA. That's the functions that run on the GPU. So to avoid confusion, I won't call it kernel. What's the other one they call it? I'm not sure. But actually, there's an operation in math called a convolution, and it's the same as this, except we're only doing it with one dimension. So like we're only outputting to one value, and makes it simpler. If you just do a element by element multiplication and then sum them together, you get a one-dimensional convolution. Which is to say, like, your output's just a scalar. Because they get more complicated, trust me. But not in deep learning. First layer, filter, dim. 3. It's the same for each layer, but we'll characterize all of the layers independently, because in our other architectures we might want to change it. Let's see, what else do we need? For our first layer, we're gonna have the slope of the Mick ReLU. So we'll have the same slope if it's above 1, and the same slope if it's below 0. If it's between 1 and -1, or we'll have the same slope if it's below -1. If it's between -1 and 1, then the output just equals its input, so slope of 1. So we'll define that here. Define activation slope. And we'll use the same activation slope for all layers. Let's do 1/100th. So we'll do the inverse here. And we'll just have 100. Oh, and then we'll cast it to a the type of float that we're using. I'm using a 16 series card right now. I do have later cards that we or like later architectures that we can use. But for now, just for the most compatibility and ease of use, I'm going to use what the 16 series has, which is the same as what the 10 series has, which is accelerated half precision floating point mathematics or arithmetic. If you have an older card, you might be better off just using regular floats. Because of that distinction, I'm going to make I'll make a type def for the type of float that we're using within our neural network, so that can be changed later. There's newer cards that actually support even newer floating point numbers like FP8, and there's also int8, which I don't think. Yeah, my card definitely doesn't support 8-bit floating point. So if you're on one of those newer cards, if you have a Hopper card, then use then change this line here, and you'll have it be even faster. Okay, we need to include a file that defines our floating points, which is CUDA fp16.h. CUDA fp16.h. And now we will type def. We'll say half as neural network float. I don't want to call it neural network weight because our biases will be the same. So we'll use this to define, or to type all the floats that we're going to be using. Also, this card doesn't have tensor cores, so I can't do the tensor core math for the neural network, but we'll just get it started using just typical serial instructions, serial per core. And then later I'll do tensor. I'll use the tensor cores. I have a Jetson Orin, so we'll be able to run it with that. But if you have a 10 series or 16 series, you can't run them anyway, so this code will work on your GPU for now. I'll try to make them cross-compatible because I'm making it compatible with this slower method in the first place. Okay, our activation slope inverse is 100. We'll cast it to this type of float. Actually, we'll just use a function casting syntax. I think that's all we'll need, so let's get started. Oh, also, it's interpreting this as a C++ file because it ends in .hpp. It'll auto-detect files that end in CU. The VS Code will auto-detect this as a CUDA file. HPP it won't, so we'll go down to the bottom right. Can you see? My mouse here. Click this button and we'll change it to CUDA. So this little button down on the towards the bottom right. Oh, and we're at not Win32, we're at 64. Oh well. Or maybe Win32 just means compiling for Windows in general, and they didn't change the name for 64. Yeah, okay. So our toolkit is for AMD64. Good. So I'll make our kernel global run neural network. Oh, we need a return type void. Actually, before we do this, we'll define our data structure of our neural network. And VS Code does not autocomplete the semicolons that you need for structs. Okay, so this neural network structure, it's going to hold all the data of our entire neural network. It's going to be really huge. And it only needs to exist on the GPU. So for our first block of data, we'll have the input. So neural network float input. The size of our input will be our input size. Oh, we need to define our channel number, or the number of channels we have on the first layer. So first layer channel amount is 32. So we'll have our input layer. And then next we need our kernels, or I mean our filters, which will be a 3x3. So we'll make a second struct for our filters. Filter 3x3 because they'll all be the same size. We could template this. Yeah. Neural network float. It's a 3x3, so we'll have 9 of these. Oh, which is already predefined for us. Oh, not neural network float. So we'll have our 32 filters here. Each with 9 weight values. So next we'll need our output layer. This will be before we do the batch normalization or the ReLUs. So let's name it raw output. And the size will be first layer output size. Let's see, to do our batch normalization, we could just use a raw output. Oh no, but when we do the back propagation, we'll need to know the outputs, the raw outputs, as well as the resulting ones. Okay. Norm output. I think we'll need to store our normalized output. We could just reverse compute from the after activation to the batch normalization output. Oh, we'll just separate it for now. And we'll have our activation output. Oh, and then but these are all for the first layer. Okay, so we'll just do the first layer right now. Now for our kernel, we'll be passing in a pointer to a neural network structure. And that'll have all of these data segments for us. So first thing first, we'll get our thread ID for each. Oh, let me add a CUDA runtime. Oh, this is our header file, so we can press Alt O, the letter O, to go from our header to our implementation, and vice versa. To our Linux directory separators. And here we'll have to have our CUDA runtime. And our cooperative groups. I don't know if we'll need driver type, so we'll take them out for now. See if it compiles. So this is commonly how you find out. So your CUDA function runs. This will launch on your GPU. And in fact, there's not a lot of overhead to launch a kernel. It's much less overhead than it is to spawn a thread on Windows on your CPU, that's for sure. But it's decent. If you can get away with if you can just launch one and run it continually, you do get a bit of a performance benefit than skipping out of a kernel and hopping back in to different kernels often. Well, first we need to populate our neural network, so we'll do that first. Also, let's namespace this. I don't like that there's some red squigglies here. Cannot open source file. This does compile though. Okay, so since this is just a test, we'll populate our inputs. So if our thread number that we're running, so just as a reminder, all of these threads are running at the same time, or all threads on a warp. So a group of 32 will all be running at the same time. And possibly if you have high occupancy, all the cores in your CPU will be running. So for our input, we'll say the size of that is input size. And we'll just make them 1. Neural network float 1. Now we'll need to populate all of our weights for our kernel, or for our filters. Neural network. What do we name this? It's not auto-completing. First, we'll need our indexes. So for our channel, we'll just take IDX modulus first layer, so modulus 32. Well, to do that, 32 is a power of 2, so we can just chop off all the bits that are above 32. Let's see, 32's 1, 2, 4, 8, 6 bits. Let's count this out. We don't really need to optimize this since this is just populating the neural network, but well, let's do it anyways. So for our weights, we'll take our IDX and divide it by 9. Oh, now it's auto-completing. And we will set, let's not set the weights to 1. Set it to 0.9, so we'll, we can set them to we set them to 0.1 because there's 9 of them. So then the result, they should all add together to be 0.9. set to 0.1, or we could just do, yeah, let's just do 1 divided by the number of weights there are plus 1. This is a float here in an arithmetic expressions. So if you ever have a float in arithmetic expression, then all the numbers after it will be converted to floats. This isn't really that efficient because we are not coalescing our weight index, our weights. But then we lose this optimization, but that's actually probably not as big of a deal. Yeah, let's flip this around. Okay, so all of our weights will be next to each other. Let me make sure I have this right. I don't think I do. So we'll do weights 0 through 1, or 0 through 8. Oh, yeah, we'll divide it by 9. Of course. And then also this should be, we'll use our defines for this. Okay, so say like indexes 0 through 8, the weight indexes will be assigned 0 through 8, and the channel index will be 0, because 0 through 8 divided by 9, integer math, it gets truncated to 0. Then from 9 to 17, it'll be 1, channel index will be 1. Then from 18 to 26, that'll be 3. So you'll see as our index gets higher and higher, our channel index will increment by 1 every 9. And our weight index will increment to 1 till it gets to 8. Then it will reset back to 0. Yeah, so typically, because our weights, whatever is the last struct you're referencing, you typically, like the way, kind of a shortcut brain-wise to think about it is that this is the index that you want to have a mod operator on. That way, and we'll go over this later, but it's an optimization in CUDA. Well, I'll just go over it slightly right now, just briefly. There's when your threads in a warp access your global memory, which is the VRAM. You know, what you see advertised on cards. Like for instance, mine's got a 6 gigabyte of VRAM, also called frame buffer. When your threads access memory, the minimum amount of memory that they can access is 128 bytes, and that's per thread. But if you have several threads accessing the same 128 bytes, then they only need to do one fetch, and then they can all read that memory. It doesn't matter. You could have also the threads, they can, all 32 of your threads in a warp can fetch the same byte or 4 bytes or 8 bytes or whatever out of that 128. That doesn't slow it down at all. It's all like instantaneous. That's called a broadcast. But if you're accessing different values in different parts of memory, or just basically different values, when your threads access it, you want them all to be together in that 128 bytes. So the best way to do that is you take, so say you're accessing floats. You have your 32 threads, and you'll be accessing 4 bytes times 32 threads, 128 bytes. Usually you would have, say, like thread 0 access the 0th address, thread 1 access like 4 bytes over, so like the second float, so float index 1. Then you'd have the third thread, fetch the float in index 2. That's typically the way you do it. In some cases, you have to, depending if you're doing the same, if you're doing operations the same 128 bytes, depending on your architecture, you might, or not your architecture, but your algorithm, you might be like swapping them around and drawing them from different areas and stuff. But as long as it's in with that, within that 128 bytes, then that's optimum. All right, we've populated our weights of our neural network. That's all we need to do for that. So that means that we need to run at least input size number of threads. As we get more and more channels, we might need to change what a number, how many threads we're launching this with. All right, run neural network. This will be the fun part. So the way we can think about this, we've got our 32 output arrays here. We'll be using 1D arrays and then converting them to 2D, essentially just using arithmetic, integer arithmetic. You have these 32 that you just add up all together to get our output. But also what we're doing is we're running each of these weights over most of our input. That's the output over our input. So another way to think about it is we just take this top left square here, and first we apply it here, multiply, and we'll get per filter, we'll get 9 output arrays. Not these 9, but we have 32 here, but for each of these 32, we'll have 9 that get added together. So 9 times 32, 270 plus 18, 288. We'll be ending up just taking 288 of these 26s by 26s and adding them together. So this top left block will start here. We'll iterate across this array, but then we'll stop here because we're not going to have our filter move to the right of here because these other blocks are in the way. We could pad around the around our input array with like a size of 2 on each side, so like 4 total, but 2 on each side. We could just surround it with zeros, and then we could get our kernel to reach all the way to the side and then just input those zeros. But I don't like doing that for one thing. We're going to be reducing our data size, like our array sizes as we go through the network, which is going to save us a lot of memory. Plus, I have a feeling it's going to mess with your filters if you like just suddenly have a bunch of zeros that are like a striking difference. Say we're doing like our artwork and you have like a blue sky and then like green grass on the bottom or something. It's all blue and then suddenly it'll just turn like completely black in a vertical line, which isn't meaningful. It's just the edge of the picture. So if our network, we're trying to create any like vertical filters that would interpret like a change in vertical colors, like or a change, you know, from left to right in your coloring and also in a straight line vertically. If we were to interpret that as meaningful, then during training, I feel like constantly reading the edges of the photo would mess it up and prevent it from training in that fashion. So I don't think it's a good idea to do that. So because we're adding all of these up, we can't do that in parallel. Well, we kind of can, but to make the most use of our threads, as we add in numbers, we can't add two numbers and then put them into the same place that like we're adding another two numbers and writing them to. So if we're doing like 3 plus 2 plus 4, or we have a 3, a 2, and a 4, and we're trying to add them all up and with different threads and output them to a single cell, you might have one thread do a 3 plus a 2, and then another thread do like the 2 plus the 4. Then you have an issue if they both write to the same output at the same exact clock cycle. You'll have the wrong value written to it. It won't be the result of all three being added together. So we do have to do these one at a time. But we got a way to still parallelize it because we are outputting in total to 26 by 26, which is what would that be? 220. 676. $26 times 26. Yeah, 676. We still have 676 elements we're outputting to, and so we can do all 676 of those in parallel. Or we can accumulate those, our 288 values that, or like additions that we'll be doing for each one. We can do all 676 of those processes in parallel. So we do get a good amount of parallelism. Not ideal because I have, I think, 1,536 cores. So we won't be using all of them at the same time. But as our neural network gets super huge, we will be able to do that. Plus we'll have, this is just our MNIST example. When we make a huge neural network, we'll be able to fully saturate all the cores. Okay, so we could do a for loop. It's not auto-completing. That's kind of annoying. So we'll have two embedded loops, one for our 32 channels and then another loop inside of that for our 9 weights of our filter channel number equals 0. Channel number is less than first layer channel amount, and then channel number plus plus. Actually, I'll just copy this. Much faster. I drop time. Alright, this might take a little thinking. While I do that, pee break. Okay, first thing we need to do is make sure that we're not running threads that will exceed our output size. Let me change this to channel index. I think that's a more proper phrasing. Because number could mean amount. Okay, so our output's 26 by 26. So we want to make sure none of our threads are higher than that. Let me check my audio is still working. Yep. Okay, so first layer output size. No autocomplete. First layer raw output. And we'll be doing it a plus equals. Oh, you know what? We should set these to 0. I think with your kernels, I think when you allocate memory on the GPU, it might be guaranteed to be 0. Let's check. I know when you have global memory in C, or you have a global variable, it's guaranteed to be 0. It might be kind of goofy if we don't allocate it to 0 anyway. So let's just allocate it to 0. Let me check I have these names right. First layer raw output. Oh, it's not. I don't have structs with instructs here. I suppose I could. We could just have a struct of for a first layer. Nah, no need. Unless someone gives me a convincing argument. I really wish autocomplete worked on this. And we'll do this to all of our outputs because we will be summing all of them. Oh, no, you won't. We'll just sum to 0 anyways. This is only run once. Our populate function. Oh yeah, we have a raw output, then we have our norm. What did I name it again? Yeah, norm output, then activation output. So we'll be using our weight. Here's where it'll get interesting. I'm trying to think what we name it, but so we'll have something like input index. So which element are we reading from our input array? Which will depend on the weight, but not the channel. our input index will be, oh, we'll have to break it down into X and Y. So our input index X will be IDX plus our weight modulus 3. So for, if we're at weight 0, of our filter, we'll be reading this element. If we're at weight 1, we'll be reading this element. If we're at weight 2, we'll be reading this element. And that's for our first, that's for our first thread. Our second thread, we just, or say it's like our 5th thread, we'll just be taking our IDX and then adding 4 to it. And reading that for, and then adding what our weight number, you know, modulo 3. And for our second layer, we'll call that our Y index, and we'll use positive. So to the right is positive X, down is positive Y. Our Y index is going to be our input index plus 28. So the dimension here, plus, you know, our weight modulo 3 again. It's going to be IDX plus input dim times our weight index divided by 3. But what if our IDX, well, it'll be our X will be our IDX modulo first layer output dim plus our weight index over 3, which is our first layer filter size, or first layer filter dim. It's almost easier to do it with the actual numbers than these names. Yeah, because if we're at IDX is 26, then this would be 0 plus 0, yeah. Our input Y will just be our input, yeah, will be our IDX divided by our input dim. plus yeah, our weight index divided by our filter dim. I think so. That means our ultimate input index will be our input index y times our first layer output dim plus our input index x. And we're doing our convolution, so we multiply it by each filter. So we just use channel and weight index here. First layer filter, channel index, weight index. This doesn't have to be coalesce, these reads. A shortcut of thinking about that is because these variables here are from the for loop. So each of these all of the kernels that are all of the CUDA kernels that are running at the same time are going to be using this same numbers here. So it's going to be a broadcast. So you have one memory address of these half floats going to all threads. There's no point in like trying to coalesce a memory read because we still have to do this 288 times. And if you go out of your way to pack it in a way where it's coalesced, you still have to read from the same 128 bytes like 288 times. So let me just think about this. This should be input dim. And this should be output dim. See our input index y. I could break this down even more for clarity. But nah. Yeah, this is a striding with a stride of 1. Across our input. So if we're at this IDX, Well, RDX is based on 26 by 26. Okay, yeah, this is right then. Pretty sure. And now we have to synchronize. Cooperative groups. What do we have here? Grid group. Equals this grid. Okay, and because in Turing, our threads in our warp are no longer guaranteed to be on the exact same instruction on a given clock cycle if they're not sleeping. So we need to synchronize before we do all these add operations. And just as a test, we can print this. What I want to do too later is output this to a CSV file and we'll check it in Excel. But for now, just to do a quick test, we'll just print it straight out of the kernel. Printf. I wonder if you can print a half float through printf. I bet you can. All right, so we'll print our output index and then our floating point output here. And just all in chaotic order. And then we will return. All right, now let's go run our kernel. So we check our status. Then we will, we have our neural network thing included, our MNIST neural network. So we've got our namespace, which is neural network. Populate neural. Well, we have this namespace here, so let's shorten down this function name. Run neural network and populate. Also, first we have to allocate in our GPU the memory for our neural network. So we'll say neural network. That's the namespace. So we named our class neural network. We'll just say that's, oh, and it's a pointer. Let's name that neural network, or NN for neural network. So now we have to CUDA malloc. We give a pointer to our pointer, and then the size we want. So size of neural network. Let's rename our class to Just capital NN. Actually, let's use our functionality here, NN. Oh, we have to select it. Yeah, the auto, or the... like the find and replace, like the tooling, it's just not working really well. I don't know why. But at least I can check mark them. Somewhat more convenient. Okay, let me double check the types here. And then looks pretty good. All right, Malik. Now we're ready to go. So normally after you do you allocate your memory on the GPU, you would copy CPU data to it from your CPU code using CUDA memcopy. But because we're generating our weights in our kernel, we're setting all of our neurons to 0. We don't need to do that. Okay, here's another thing we're gonna do with our, we'll make an error checker. But this one will be special. Okay, we're gonna make this macro. If we're in debug mode, it'll run CUDA check and CUDA device synchronize. Because if you have a memory error in your kernel, it won't tell you until you check an actual CUDA call to the through their API calls, not just your kernel calls. But we don't need to synchronize though. So when we're in release mode, we don't want to do that if it's not necessary, because we haven't put a stream number on these kernels. Oops. Then they're all running. They won't run in parallel. They'll run one after another. So there's no need. There's no need to synchronize them, so we'll only synchronize them if we're in a debug mode. Okay, now the number of threads we're gonna run. We're gonna make a file called CUDA helper, and this will help us determine how many whoops. This will help us determine how many blocks we're going to run. Given we want to run so many threads, we're running so many threads per block. We can just tell it how many threads we want, and then our function that I'm going to make here is going to tell us how many blocks we need then. So pragma unst. Copy relative path. I don't think we'll need any standard library. But our function name will be num blocks. So we'll put in how many threads we want, and it'll output to us the amount of blocks to use. Oh, to do that, we need to know our block size, which is a neural network, which actually probably shouldn't be in here. Well, let's make a config file. Config.hpp pragma unst define. Whoops, wrong line. This block size is more of like a GPU performance thing than it has to do with a neural network. So I'll make a configuration for it. We'll put other variables in here too. Config.hpp. Copy relative path. Go to CUDA helper. And there we go. Int num blocks will be the number of threads we have minus 1 divided by our block size plus 1. And that's our value. Okay, so what we want to do is we want to have like, so say we have 256 threads we want to run, and our block size is 256. Well, in that case, we want to run one block. But if we have 257 threads we need to run, well, now we have to run 2 blocks. And if we have like 255, then we still need to have 1 block. So what this does is if we do 255 minus 1, that's 254, divided by our block size of 256, that's 0. So we adds 1, that brings us to 1 block. If we have 257 though, then that'll subtract us to 256, divided by 256 is 1, and then we add 1, and now we have 2 blocks for our 257. I'm sure there's a way better way to explain that. But it's getting late over here, and we got things to do. We want to run our kernel. So that's our CUDA helper. Copied relative path. Then we'll take our implementation file, copy that path. This will be on both our, we'll use CUDA helper with our debug and our other project. I mean with our mnist and our main project. So here we go. So I'll have to run CMake again. Ooh. Okay, so num blocks to populate. Let's see how many we have here. We have first layer output size, first layer channel amount times first layer filter size. Basically just the maximum of all these values. We should make a function where we just put in max. But we'll do that later. So we're running this many threads. And then I believe with our run function, oh, it code navigated. That was nice. Just doesn't autocomplete. Looks like we have first layer output size here. Okay. So we have to CMake it. Oh, which automatically happens for our mnist project. We got some errors. Oh, struct and semicolon. I'm so bad with that. The semicolon after struct. Well, it doesn't autocomplete, and I don't really see why that's in the rules that you have to do that, but oh, whatever. First layer output size is undefined. Neural network. Oh, okay, because I need to square the dim here. Okay. That looks good. Input dim squared. First layer filter size. Let's try it again. Block size, that's in our config. Which is in our CUDA helper, I thought. Oh, but only the implementation. I'll kind of sort these by the order we use them in. Save and CMake build run. Oh, that's right. We don't have our error checker. I'll just kind of alphabetize these or use them in the order we'll do a hybrid sort on our headers. Okay, more than one operator backslash matches these operands. I haven't seen this before. Maybe we do need to cast this because this isn't a typical float, it's a half float. So it looks like it has some kind of special rules. And it's saying first layer input dim is undefined. Oh, that's because we don't have it as first layer. It's just the input. Oh, this is building a regular project. We don't want that. We want 0.5. Okay, looks like on line number 28, we're catching an error, and it is right after our run function here. Actually, you know what? I don't like this, the way this error message is. Let's fix that. For line number, we'll just put a colon after it. That's like common with no space. That's like the common format for listing a line number. Okay, CUDA error launch failure. Why could that be? First layer output size. Could it be our printf? Since we're outputting half floats? Nope. I wonder what could cause this error. Oh, here we go. It gives us common issues. An exception occurred on the device while executing a kernel. Common causes include dereferencing an invalid device pointer and accessing out-of-bounds share memory. Less common cases can be system-specific. More information about these cases can be found in the system-specific user guide. This leaves the process in an inconsistent state, and any further CUDA work will return the same error. To continue using CUDA, the process must be terminated and relaunched. That's fine. We wouldn't want to keep running it with an error like that. mnist main. Okay, so we're probably we're not using shared memory. First layer output 26 by 26, which is 676. 256. So there'll be 3 blocks running. And for us to be out of bounds. So our output, so we're referencing our output, which is within first layer output size. So we'll just print if input index is greater than our input size. We'll just print a thread ID %d input size. Now our channel index won't get above 32 first layer channel amount. Let's make sure this is filled in correctly. First layer channel amount. Weight. First layer filter size. This is 9, that's good. And our weight index will not go above first layer filter size. Okay, so it's probably our input formula here. If our input index is greater than input size. Okay, let's try it out. I'm kind of concerned though. So it didn't print out anything, but that might be because it's erroring out on the next line. So it kind of just shuts down. So I won't access that. By commenting it out, let's see if it prints. Okay, still. Okay, yeah, now that we put the colon without a space, we can click to it. That's really cool. Yeah, it's happening after run, but not after populate. But now we're not accessing. Oh, you know what? Okay, because we're not calling it as a cooperative group. That's probably what it is. Whoopsie daisy. So we'll say void pointer neural network run. Our grid dim will be our number of blocks, and our block dim is our block size. And our kernel args, oh, we have to do some fancy footwork for that. Equals a pointer to a pointer. Okay, yeah, so we get the pointer to our GPU memory pointer. And well, we just chuck that in this. All right. Okay, no errors this time. Now let's actually try printing this. Also, it looks like our input size. Nothing exceeded our input size. None of the input indexing. All of our values are 0. We want them to be 0.9. Because we're taking our input, 1. We populated all of these with 1 over 9 plus 1. So 1/10. Let us look at what our input index is going to be. We should get all kinds of numbers. From 0 to 783. This is in like an embedded loop though. So let's do, if our weight index is equal to our, let's just check our last loop. And our channel index is equal to our first layer channel amount minus 1. Oh, and then we'll get rid of the input size check since we know that works. So the last weight of our last channel but all the input indexes. So it should be like, let's see, 28 plus 56 plus 2 is 58, subtract 1, 57. Should be none less than 57. and all the ones from a factor of 28 plus 2, 2 that plus 2. I'm not seeing all of the threads, but well, let's not print this. $58. At thread 0, it's 58. That's what we want. $58 plus 28, 86. Yeah, we wanted 83, 84, 85. Yeah, it skipped 84 and 85. That's what we wanted too. So that seems like it's correct. These are all ones. And these should all be 0.9s. Am I printing out first layer raw output? Yes. Let's just make sure that printing half floats works. Okay, so I'm setting all the values to 5, then I'm going to print 5. Yeah, it doesn't print them. So my code was right the whole time. As usual. It's giving us a warning here. Argument is incompatible with corresponding format string conversion. Okay. That solves it for us. And so... oh, what if we just cast it to float? Try that. Okay, that worked. Let's try it with the actual values. 28.16. Oh, that's right, because we're adding them together 32 times, so it'd be 0.9 times 32, which should end at an 8. Pull up our calculator. I got a calculator shortcut button on my keyboard because I'm a professional. Okay, 0.9 times 32. 28.8. It's probably the loss of precision in a half float. Adding a bunch of small half floats together is kind of a bad way to do it. As the number gets bigger, you can multiply and divide floats without losing, or without having to worry about precision. Well, I mean, you do a little bit, but when you add is when it gets really bad. As your number gets larger and you're adding small floats to it, the rounding error can get pretty terrible. So there's ways we can work on that later. We can add a bunch of small floats together. We can just take pairs of small floats and add those together. And then we'll get half the amount of values. And then we can take those pairwise and then add those together and get half the amount of values again. And then like keep crunching them together like that. And that'll help our precision losses. But hey, though, it's working. So that's our first layer, convolutional neural network. Next time I'll make the activation layer. And we know this works, so it'll be pretty trivial to add in our next 9 convolutional layers. And we could even add in the fully connected one too. That one's also not too bad. Better, it's easier than convolution. So we'll do that. For batch normalization, let's hold off on that a little bit because I don't really feel like doing that. We need to make a summation kernel that's efficient. Well, which we need to do for this anyways. But we'll do that. We'll do that after we do activation, and we'll make the whole network. We'll not have batch normalization, and we'll add that in later, just so we can get a lot of work done. All right, I'm just checking out my stream. I've got no patrons left yet. If anybody wants to subscribe on patreon.com, any donations are appreciated a lot. And that'll help me continue this project. And yeah, besides that, we got a lot done tonight. Didn't run into too many problems. So with that, I hope you enjoyed it, and happy coding.